Chapter 6 Laplace Transform. A Laplace transform is a technique to solve this equation. It's particularly useful for discontinuous. Remember, if we solve a discontinuous g, then we have to solve it segment by segment, and using the end condition of one segment as the initial condition for the next segment. Right? Using Laplace transform, we can solve the whole equation, including the initial condition, with one big solution. Okay, well, with one big step to get the direct solution. And let's see how we do that. So first, let's introduce the transformation itself. Then we will see how to use this to solve the differential equation. The definition is a bit different from what we have seen so far. It involves an integral. So, since this is for engineering application mostly, we will just interpret t as time and s as the variable that you get after the transform. So the transformation turns a function of t into a function of s. So it's not like a function itself; it's a operation because you inputted the function, output is also a function, but within different variable. So you can see for every s, you have a function of s and t, which is just e to the negative st. You times that, you get a function of s and t, but after integration, you get only s. So that's why we have the function of s. And let's just see some examples, so how it works. So let's see, what do we have if we plug in 1? Okay, just 1. So f is identically 1. Alright, how do we do that? That's e to the negative st over negative s. Well, then immediately you run into a problem. You have to plug in infinity into t. So you have e to the negative s times infinity. And what is that? Well, it depends on the value of s. If s is positive, then you have negative infinity. So that's 0. Right? And if s is less than 0, then this is positive, so this is negative infinity, so you get infinity. Well, certainly we don't want to involve the second case here, so we want to only work with positive positive s. Then you can say you plug infinity, you get 0, right? And then plugging the 0, you will get 1 over negative s. The answer is 1 over s. So this tells us that Laplace transform will convert 1 to 1 over s, provided that s is positive. And this condition may depend on your function, but it's always s for some positive s value, or a large s value, because if you have a large s value, then you have a fast decaying function, so more likely you will end up with a finite integral, right? So let's see. Let's introduce a new notation. Since this transformation will convert a little f to a capital F, we denote it by L. And input is f, the output is capital F. Alright, so when we say L of f, it means integration of e to the negative st ft dt. So the output would be a function of s. Okay, so in this notation we can say L of 1 equals 1 over s. And the condition is s is greater than 0. but usually we will omit that, just say this is true for sufficiently large S. Alright, let's see another example. F equals e to the at, and a is a constant. So let's see what is that. 0 to infinity, e to the negative st, e to the at dt. And you can see the best way to do it is not to regard them as a product, but as a single term. Okay? And why can we do that? Oh, no, why is this good? That's because this, it's just like our new S. Remember what we used to have this in our last example, right? No, just regard this as a new S. So the answer is just that. Okay? But the condition is also changed. That's a condition. Or in other words, it's that. Right? So it means the answer is 1 over S minus A, provided that S is more than A. And if A is positive, then A is more than a positive number. If A is negative, then S is more than a negative number. So you can see this condition depends on your function, the input function. But it's always S greater than something. So we will just, from now on, ignore this condition. We'll just say out of e to the at equals 1 over S minus A, provided S is large enough. Alright? So we have seen two functions. And let's see another function, t. Yeah, a very simple function. And then let's see what we have. E to the negative st, t, dt. Well, then you have to use integration by part, right? So you have, oh sorry, positive integration. You want to integrate e to the negative st first, because if you integrate t first, you get t squared over 2, which is more complicated. So you have d, what's the integration of that? Right? Then let's write down that uv form, minus e to the negative st over negative s dt, right? And you can see this negative cancels. And if you plug in infinity here, you get 0 for large S, and plug in 0 here, you also get 0 for t equals 0. So you only get the second term. And what is that? You see the S is constant. You can factor that. Okay, and guess what? This is something we have just done, like 5 minutes ago. So this is 1 over S times 1 over S, get 1 over S squared. And this thing is very typical, meaning, we will get integral into something that we have already seen. Okay, so that's 1 over S squared. Now let me summarize what we have. Out of 1 equals 1 over S, out of e to the at equals 1 over S minus A, and L of t equals 1 over S squared. Okay, so we have 3 terms in our family, and we will have more and more. Okay, now let's see L of t squared st times t squared. Alright, then let's say integration by parts will give you t squared. Okay, then you have this minus, switch them, d of t squared. And what is d of t squared? It's 2t dt. Alright, and once again, plugging infinity, you'll get 0. Plugging 0, you also get 0. And this negative cancels. You can factor out S, and you can also factor out 2. Right? Then what's inside? Aha, do you see that? That's nothing but L of 1, L of t. And what is L of t? Here. So what do you get? 2 over s times 1 over s squared. You get 2 over s cubed. Okay. I have one more family, one more member in our family. Okay. So you can see we have constant exponential function, power function, and we will add sine and cosine in the end. So eventually we'll have all the elementary functions. Okay. Now let's see what is L of t cubed. And if you recognize the pattern over there, you will see it's kind of the same story again. So let me just write down the UV part directly. Okay, so t cubed times e to the negative st, and this is negative s, and minus e to the negative st, negative s, then d of that is 3t squared dt, and this cancels, and the first term will be gone, right? And because this is 0 and that's also 0 when you plug in the limits. So you factor out 3 and s, then what's left is just the t squared down there. And then you have 3 over s times, what is L of t squared? It's 2 over t cubed. 2 over s cubed. So you have 6 over s to the 4th. Well, if you can observe the pattern, you will see we have a general formula now. Can you see what it is? First, s to some power. And that's not n, it's n plus 1, right? Because this, for t cubed, it's 4. And the numerator is 3 times 2, and start with n, so it's n factorial. Okay, so we can write down our family in this simple way. No, sorry. At equals 1 over s minus a, and L of t to the n equals n factorial over sn plus 1. And you can regard this as a special case of either this one or that one. Why? Because if you choose a to be 0 here, then it's 1, and that's 1 over sa. That's 1 over s. And here, if you choose m to be 0, then this is 1, and this is 0 factorial over s, which is 1 over s. Okay, so you can say this is our member, and this is a special case. Now let's find out the sine and cosine. Let's say, what is sine of at? It will be e to the negative st times sine of at. Well, that is something a little bit harder, right? Because we can do integration by parts, but if you remember, we will not get a result directly. We'll go back to self, then add together, divided by 2. So let me call this I. Let's see what it is. Let's choose to do the same thing. So we will have sine of at, then d of e to negative st over negative s. And then you have a sine of at times e to negative st over negative s minus e to negative st over negative s. Then have derivative, which is a cosine at dt. Right, same story again, because you can plug infinity, you get 0, plug in 0, you get 0, and this cancels. You have 1 over s, then factor out. We have also have a there, so a is also outside, and then e to negative st cosine at. So you can write on this as a over s times L of cosine at. Well, there's a little problem because we don't know what L of cosine at, but we know we will go back to sine of at. So let's do it this way. L of cosine at equals what is that? Cosine at. So you will have cosine at e to the negative st over negative s, right? And then you have cosine at e to the negative st over negative s minus, switch them. D of cosine at is negative a sine at dt. Alright, now you have to be a little more careful because if you plug in limits, infinity will give you 0, but 0 is not 0. What is cosine 0? It's 1, right? And what is that? That's 1. So you have negative 1 over s, but it's in the lower limit, so it's positive 1 over s. And then also careful here, we have plus and a plus, but you have a negative a, so you have a negative a, and then you have sine of at. Okay, so let's see what we have. We have sine L of sine at equals this, and L of cosine at equals that. So actually we have two equations. L of sine at equals what do we have? A over s. L of cosine at, and L of cosine at equals 1 over s minus a, oh sorry, I missed an s here. So you have also a over s. A over s, L of sine at. Okay, so we have two equations with two unknowns, and then let's solve them. Say you want to solve for sine of at, then you multiply the second equation by a over s, right? Then this left side will match the right hand side, so you will have L of sine at equals a over s squared minus a squared over s squared L of sine at, right? And we can multiply s squared on both sides. A minus a squared L of sine at, and you can move this one over there, so you get L of sine at equals a over s squared plus a squared. Alright, that's what you have. And similarly, you can have cosine at, and actually you can do it directly because we know a simple relation. If you know L of sine at, you can just times by s over a to get cosine part, right? S over a. So s over a times n. Alright, that's our pair. The denominator is s squared plus a squared, and numerator is a and s. It's easy to remember which one is which, because you can plug in the special case of a equals 0. If a equals 0, what do you get? Sine of 0. Of course, that's 0, so it's a. And if you plug in a equals 0 for cosine, what do you get? You get a 1. What's out of 1? It's 1 over s. So it's s over s squared, so it's 1 over s. Okay, so sine at is a over the square, sum of the squares. And for cosine, it's s over s squared plus a squared. Alright, that's our complete family. Now let me put them all together. Out of e to the at equals 1 over s minus a, and the e to the t L of t to the n. It's n factorial over s to the n plus. Okay, so that's the entire family of solutions of Laplace transform. In the next class, we will see more transformations. Say, if we combine this with that, sine times exponential or exponential times t, sine times t, we'll get an even larger family. All right, that's it for today.